Hi, my name is Tammy Miller. In this common ion effect video, we're going to calculate the molar solubility in the presence of a common ion. When a common ion is in a solution, this means that it is going to lower the solubility of the solute that we are adding. Because of this change in the molar solubility of our solute that we're adding, the concentration of the common ion must be accounted for in these calculations to show that change or that lowering of the solubility. There are some specific steps that we need to do to calculate the new molar solubility when a common ion is present in the solution. These steps are very, very important for us to follow. When we don't follow these steps, we end up with the wrong molar solubility. So the first thing that we need to do is always write out the balanced chemical equation that is for the dissociation reaction of the solute that we're adding. Next, we set the molar solubility equal to X and determine how much of each product is produced by the dissociation of the solute. This is no different than normal calculations for molar solubility. The third step is different, however, and I want us to really make note of this third step. So this third step here, when we have a common ion, we must add the concentration of that common ion to the X for that ion. Then we plug this into the KSP expression and solve for X. So the third and fourth steps here are just slightly different in that we're going to have numbers instead of an X. One of the things that we need to realize when we are adding the concentration is that the X that will be in the solution from our solute will be negligible. So this concentration is going to be very, very high. And because that concentration is high, that is the only thing that we will add. We're going to look at how to do this in a couple of problems to make sure that we understand how it's going to work. So the KSP for silver chloride is 1.8 times 10 to the negative 10. When silver chloride is added to pure water, the molar solubility is 1.35 times 10 to the negative fifth molar. What is the molar solubility of silver chloride in a solution of sodium chloride? So the first thing I need to do is I need to note that I have a common ion. And my common ion here is going to be the chlorine ion that is coming from sodium chloride. So I'm going to follow the steps we talked about. The first two steps are going to be the same as any molar solubility problem. First thing I'm going to do is I'm going to take my solid silver chloride, my solute, and I'm going to dissociate it into its ions. That is step one. In step two, I'm going to write my KSP expression. So my KSP is the concentration of the silver ions times the concentration of the chlorine ions. Now, I know that the silver ions are going to be X. The chlorine ions is going to be a little bit different. The chlorine ions is going to be 0.1 molar plus X. And that's because we're told in the question that we have a 0.1 molar solution of sodium chloride. So that means that there's a concentration of 0.1 molar chlorine ions already present. As I mentioned, this is going to be a very, very high concentration. So technically, we can ignore this X. And so what we'll be adding is a concentration of 0.1 molar. Now, I plug in my silver and my chlorine into my KSP expression, and I end up with 1.8 times 10 to the negative 10. This is the KSP they gave me in the question, is equal to 0.1x. I chose to take 0.1x and put it into scientific notation. So it's 1 times 10 to the negative 1x. I'm going to divide both sides by that to get x by itself. And I'm going to end up with 1.8 times 10 to the negative 9 molar. This is now the molar solubility for my silver chloride. And I want you to note something. This is significantly less than the 1.35 times 10 to the negative 5th molar that they gave us in the question when silver chloride is added to pure water. I know I've done this calculation correctly because the molar solubility has decreased. Let's try a second problem. What is the molar solubility of iron 3 hydroxide in a solution of pH 11? The KSP for iron 3 hydroxide is 6.3 times 10 to the negative 38. Here, we're going to go ahead and do the first two steps like we know how to do. So the first step is we're going to write the dissociation of our iron 3 hydroxide solute. We find out that we get 1 iron 3 ion and 3 hydroxide ions. So when we write our KSP, we have the concentration of our iron 3 ion times the concentration of our hydroxide ions to the power of 3. Remember that that 3 becomes an exponent. When I look, I know that the iron 3 hydroxide, X means ion. There is 1 iron 3 ion, so that's going to be X, and there are 3 hydroxide ions, so that's going to be 3X. But I don't yet know what the concentration is of the hydroxide ions that are in the solution. So I have to figure that out using the fact that they tell me that this is in a solution that is a pH of 11. So we're going to do this over on the right. I know that pH plus POH is equal to 14, which means POH is equal to 14 minus pH. They tell me my pH is 11, so I get a POH of 3. Now I need to figure out the concentration of hydroxide ions. So I know that POH is equal to the negative log of hydroxide ions. To get a 3, this means that it's going to be the negative log of 1 times 10 to the negative 3. So my hydroxide concentration is going to be 1 times 10 to the negative 3. That's what I'm going to add to my 3x. Now, this is a very high concentration, which means my 3x is negligible and can be removed from the calculation. So now I plug these into my KSP expression, and I need to cube my 10 to the negative 3 to give me 10 to the negative 9th. So they tell me my KSP is 6.3 times 10 to the negative 38, and I have x and 10 to the negative 9th. I'm going to divide both sides by 10 to the negative 9th to isolate my x, and I find out that my molar solubility is 6.3 times 10 to the negative 29th molar. At this point, I am done with my calculation. This is going to be significantly lower than it would be if there was no hydroxide ions around. Understanding how to calculate with a common ion and realizing that the common ion concentration is going to be significantly higher than the X that is coming from our solute is key to being able to calculate molar solubility questions with a common ion.